All right, so this whole unit is basically taking the functions that we've learned already and combine them in different ways, right? We're going to look at how you can combine functions by adding and subtracting them, by multiplying and dividing them, and what we're going to do today, which is composing them. It's when the input of one function, so let's say, for instance, your g of x function. So you see I'm sort of following this arc that goes from the first circle or first oval into the second oval. So this x that you put into the g function, right? This result that you get from the g of x function becomes the input into the f function, right? And what you notice is that at the end of the day, you have the f of the g of x. So I'll just write down again what you're seeing. The f of the g of x. So the x that you put into the first oval becomes the g of x number. So that's like your y value. The g of x is your y value. And that y value now becomes the x value, right? The input that goes into the f function. So what I'm doing is putting the g function result into the f function, and that gives me my final result. So that's what we do to compose functions. You can compose functions more than once. I can do the f of the g of the t of x. I can compose three functions at once, but it just simply means that I'm taking one function and putting it inside of another, right? The result of one function becomes the input into another function. That's the basic idea behind compositions of functions. So let's see if we can put that to make some sense of that. Given the table, f of x, right? So this table that you're looking at right here is my f of x table. That's the f of x function, and this is the g of x function. All right? Now, another way, by the way, that you can, there's another way of sort of setting it out or presenting it. Instead of saying g of f of 3, which is what you see here, is to put a little circle between the g and the f. So you'll see that as a common way to represent a composition of functions. So both of these things that you see here are identical. The g of the f of 3 is the same thing as a g circle f3. Those two ways of presenting information are basically the same. So let's now see what the g of the f of 3 is. Right? So let's first of all find the f of 3. So to find the f of 3, I'm going to go to my x line. So this line I am pointing to right here. And I'm going to find where the 3 is. So here's the 3, and the 3 points to the 1. Right? That's what the f of 3 is. F of 3, the f line, the f column, gives me a 1 when I put 3 in as my x. So that result of 1, okay, so this result now is going to become my new x, which I'm going to put into my g function to get what that result is. So this now is up here. That's my 1 now, right? Because I now need to figure out what that result is, which is 1, gives me in the g function. So I found the f of 3, which is 1. I'm going to go now back to the first column to find out what 1 gives me in the g column. So I'm going to be using this and pointing to this number over here. So the result of all of that is actually equal to 6. So let me go over that again. So circle replaces the bracket. Yes, Ryan, exactly. That's exactly right. The circle kind of replaces the bracket. So those two things, by the way, do mean the same. Let me just emphasize that. Wait, what? Okay. What Ryan is asking is about, let me just go back before we get to this answer again. The question was the g of the f of 3, and we're saying that another way of saying the same thing is to say g circle f. I don't know why I put f a different way. Circle f of 3. So that little circle that you just, let me erase this actually. That little circle that you see right here that I'm pointing to, right? That little circle means the same thing as the g of f of 3. Okay? Not Rand's question. I mean, how do you get the 6? Oh, okay. All right. All right. Okay. So let's go back and say what f of 3 is. Right? Let me erase all of this and talk about the f of 3. Right? I have two columns here that represent a function. Now, a function doesn't have to be an equation. right? I know you're accustomed to equations being functions, but a function is just simply a relationship between two things. So here's my x column, right? All of these x's are linked to all of these f of x's. So let me ask you the question, right, Natasha? What's the f of 3? What's the f of 3, right? What do I get in the f function if I put 3 into it? That's my question for you, Natasha. I get 1, okay? Now, that now becomes my x value because I want to know what happens when I take that result, which is 1, and put that as my x and relate that to my g function. So this result that I got, let me do it the way I did it before. This result that I got, right? I'm taking that now and looking for that same number in the x column, and then I'm going to see where that takes me into the g column, right? Because that's my g function, that's the g of that particular f of x. The f of x is 1, and that f of x becomes my x into the g function. So we always use this table. No, Natasha, it's not always this table because we're going to be looking at equations eventually. But I'm just showing you how the output of 1 becomes the input into the second function, or into the outside function, I should say. Okay, so let's answer Edmund's question then. So the answer to this one is 6 because let me just follow the logic of this here. Let me erase this again. Right? I'm starting off with the 3. It takes me to the 1. I take that 1 back to the x column. And then that x column eventually leads me to the result over here. So that's first of all what we're saying. Let me see if I can answer Edmund's question now. Edmund is saying the g of the f of 4. Okay. So the g of the f of 4, let me erase this now. I'm going to erase what I have here. I'm going to answer your question. I'm going to take the 4, put it into the F column, and I'm going to get 3. That 3 takes me back up to 3 in this column. And then I'm going to go across and I'm going to see that that relates to 4 in the G column. Okay? So to answer your question, yes, that's how that works. All right? And you're asking, let's see now, we're going a little too fast. Chrisania is saying the f of g of 2. Okay, so let's erase that and try that. I'm glad you're asking all of these things. So f of g of 2. Find the g of 2 first. Here's my 2 right here. The g of 2 is 5. Would you agree with me on that? Let's start with that. Christina says yes. Okay. Take that result, the g of 2, which is 5, put that into the f function. So if I wanted to find what the f of 5 was, then I'd be going over here, right? And then I'd be going from here to the result in the f column. Does that make sense? So anytime you get a result, you take that result and put that back as your x to get your next result, is what I'm saying. It becomes the input for the next round. So let me start off with the g of 2. I think we all agree that the g of 2 is 5. Can we, first of all agree on that? Yes, Mohammed. Can we agree on the g of 2? Perfect. Okay. It's 5. So let me write that down. The g of 2 is equal to 5. We've all agreed on that. Take that 5 and find the f of 5, right? Because whatever that is our answer. This thing says find the g of the function, take that g, put it into the f. So I need to find the f of 5. So I go to my function and find where the 5 is and go from the 5 in the x column over to what the f of the x will give me, which is in fact, as it says there, 5. Okay? Does that, Shiban, does that help you out? If we first of all find the g of 2, which is 5, take that 5 and put that into the x column and now go across to the f column because I need the f of that 5. The f of that 5 is 5. Is that more clear now? And Natasha, thank you very much. If I did say that, then I apologize for that. Is that more clear to everybody now? Let's just make sure that we're all clear on that. That's okay. So yeah. So if I said the wrong thing first, I'm sorry about that. Okay, let's try this one now. The f of the f of 4, what does that mean? Let me erase all of this. What do you think the f of the f of 4 actually means? In fact, I want to be able to see the table. So what I'm going to do is I'm going to bring this up here so we can see it, right next to the table. What does the f of the f of 4 mean to you, you think? What do you think that actually means? F of the f of 4. Anybody? Yeah, the answer you say is 1. It might be, but we first of all want to know what it means. It means you find the f of 4 first. Let's do that. Let's find the f of 4. So the f of 4 means taking the 4, and that takes us across to 3, right? We go from 3 now, put that as your x value, right? And then we're going to go right back again to the f column again, right? Because we're finding the f of 4 and then using that answer back into the f column again. Why do we put 3 as the x value? Because, okay, let's do it in stages then. Let's do this in stages, Ryan, right? Let's say the f of 4 first. Can you tell me what that is equal to, please? What's the f of 4? Look at the column and you tell me what the f of 4 is. 3. Okay, so I need to find now, that now becomes my new, since I find the f of the f of 4, I'm going to take that result and put it back into the f column again. F of 3. So what's the f of 3 then? What's the f of 3? And you know why I'm using 3? Because that was the result. The result of this becomes the input for that, is what we're saying. Okay, so that's why the answer is 1. All right, does that make sense? I want to make sure that we're good with that. And that was the last one on this page. Okay, now I'm going to approach this in a different way, which is, what if I gave you the function and said the u of x function was x squared plus 3x plus 2, and the w function was 1. So in other words, rather than giving you a table of values, what I'm now giving you is an equation and asking you to find the u of the w of 2. Okay, so it's not a table of values. It's just simply two functions, and I'm asking you for the composite of the u with the w, where the w is the inside function and the u is the outside function. So if I asked you to find the u of the w of 2, what would you suggest we start doing first? Right? If I just threw that out to you and said, let's do that. Find the w of 2. Thank you, Hussein. So the w of 2 simply means I'm going to take 1 over 2 minus 1. All right, that's what the W of 2 is. So that's equal to 1. Now what do I do? What's the next step in the process? Find the U of 1. There you go. So now I'm going to take the U of 1, just putting it into the U function. So it's going to be 1 squared plus 3 times 1 plus 2. And that's equal to, what is that? 3 plus 2, 6. All right. So clear enough, hopefully. Everybody okay with that? Hopefully that was even easier than the stuff we did with the table. How about the W of the U of minus 3? Let me make sure you can see the equation again. Let me bring that equation down for you. All right? So you can see exactly what the equation is. Okay? So the W of the U of minus 3. What's the first thing that we need to do? Okay, ask me to go up a bit. There you go. All right, remember, this is all going to be on the video later on. Okay, back to this. We're going to find the U of minus 3 first. Exactly. So the U of minus 3 is equal to the minus 3 squared plus 3 times minus 3 plus 2. Okay, so this is going to be equal to 9. This is going to be equal to minus 9 plus 2, which of course is equal to 2. And what do I do with that? What happens next? Find the W of 2. All right, I have the U of minus 3, and I need to find the W of 2. So the W of 2 is now equal to 1 over 2 minus 1, which of course is 1. There you go, folks. That's it. Right? That's all there is to it. So if you get so if I give you a table of values, then the table of values would be enough for you to see how to go from one to the other. The output of one becomes the input of the other. It's the same thing here when I have the actual equations. All right? Okay. Now let's see if we can come up with equations now. Can we actually take one equation and sort of put it into a second equation? So if one equation is f of x equals x squared, and the other equation is g of x equals x plus 3, determine an equation for each composite function and then graph the function and give its domain and range. So let's do that. What do you think would be the, let me bring this up here. What do you think would be the way to find the f of the g of x? So we're not talking a specific number now. We just want a composite function, a function that takes one function and makes that function become the input of another function. What do you think the f of the g of x would look like? By the way, remember that this is the same thing as saying, oh, sorry, hold on. The same thing as saying f o g of x. They mean the same thing. Just want to make sure if you see that somewhere else that it doesn't throw you off. A little circle in the middle means the same thing as the f of the g of x. Okay, so can we put the two functions together? Is that possible? And how exactly do we do that? It's probably what you're thinking it is, even though you're not saying anything yet. So let me show you. The g of x function is the x plus 3. So wherever I see an x in the f function, I'm going to replace it with x plus 3. So here's what it looks like. It's the x plus 3 squared. There you go, Christania. Well done. All right, that's what the f of the g of x function is. It's just simply taking the g of x function, which is this, and anywhere I see x in the other function, I'm just simply going to substitute that with the x plus 3. This is going into this function. That's the way it is. The g goes into the f. All right, so let's talk about domain and range now. And of course, we're supposed to sketch a function as well. All right, what's the domain of this function? Right, we've seen functions like this before. What's the domain of this function? We'll get to the range in a second. What's the domain of this function? By the way, is everybody okay with what Chrisania and Shiobon have put in? That is in fact the f of the g of x function. Does that make sense? Stop me if it doesn't, please. All right, is everybody okay with that? Or do I have to start calling out names? Okay, we can do that. No, it doesn't make sense. Well, you got the right answer though, Shiobon. What part are you not sure about? You're confused? Okay, but you got it right though. You realize you did get it right. Why? Oh, you're asking. Oh, I just realized you said, why is it x? I thought you were giving me the answer. Okay. What is the g of x function? Let's start with that. What's the g of x function, Shiobon? What does it say it is? Just tell me what it is. And Alexander, you're right. We're going to come back to you in a minute. What's the g of x function, Shiobon? Just read it off. What is it? Shiobon, you're with us, right? Okay, so what is the g of x function? Tell me what it is. Just write it out. It's x plus 3. Okay, see that x plus 3? Go over to the f of x function, and anywhere you see an x, rip it out, throw it aside, replace it with the x plus 3. Right? So anywhere you see an x in the f function, because that's the outside function, you take it out, throw it away, replace it with x plus 3. Tell me what you get when you do that. Do you not get x plus 3 all squared? Does that not make sense? What do you think? Good. Now, let's just quickly talk domain and range. Alexander has says that the domain is infinity to infinity. A good way of course, saying that is just say that it's all real numbers. How about the range of the function? Does anybody know what the range of this function is? What is the range of the function? 0 to infinity, Alexander says. Is he right? Is he right about that? What do other people think? Right? Is it that it is 0 to infinity? Come on, folks. You're supposed to be able to, you agree, Brandon says. I'll give a little sketch of this function that you should know. Let's see, I might not have any room here, so I'll put it on the other page here. The sketch of this function would be this. It's the y equals x squared line that's been shifted to the left by 3. Right? You should know that. This here represents horizontal shift to the left of the x squared function is what that is. So it's right to assume that this function is anything greater than 0, including 0. So the range of this function is that y is all real numbers as long as y is greater than or equal to 0. Okay, so Alexander's answer is fine, opens upward, absolutely. And I've just drawn you a little sketch of the function, so we're good to go. Now, is composition commutative? And what I mean by commutative is that the order does not matter. We just composed the g function into the f function. But what if we were to compose the f function into the g function? Does it matter? It does not matter, Quinn thinks. Quinn thinks that they are one and the same. So the order in which you compose two functions may not matter, is what Quinn might be thinking. What do other people think? Because we're about to do it right now. Right? We're going to put the f function into the g function. So it's going the other way now. Right? Do you think it matters, or do you think it's going to give us the same result? What do you think? It does give us the same result. It does matter. Yeah. Because now I'm going to do it this way. Right? I'm just going to take the x squared, right, which is the f function. The inside function is my f function. This function right here is my f function. That's my x squared. And anywhere I see x in the other equation, I'm going to replace it with the f function. So what it is as simple as this. It's this. It's x squared plus 3 is all it is, as Chrisania just said. Right? It's just x squared plus 3. So what I'm doing is I am taking that x squared and replacing anywhere I see x in the g function. Remember, I'm putting f into g is what I'm doing here. Right? Does that make sense, everybody? I want to make sure. So, in fact, composition is not commutative. Right? It's not commutative. So the order does matter because we're getting two very different functions here. Right? One was x plus 3 all squared. The second one is x squared plus 3. And the domain of this one, by the way, let's just talk about that very quickly, is what? What's the domain of this function? Anybody, quickly. We have quite a bit to get through here. What's the domain of this function? Nobody know all real numbers? Absolutely. So it's all real numbers. And how about the range of this function? Think about what x squared plus 3 looks like. It has to be greater than 3. Thank you very much. I'll quickly draw a little sketch of that. So x squared plus 3 looks something like this. It's the x squared function that's been shifted up vertically by 3. So y must be greater than or equal to 3 is correct. Yes. So it's y is all real numbers, but y must be greater than or equal to 3. Okay, good stuff. Let's quickly see if we can finish these other ones here. F of the f of x. F of the f of... So what does that mean to get the f of the f of x? Right? What does it mean to take the f function, which remember we said is x squared, and put it back into the x function? So look at what Brandon just said, right? He's taking the x squared and putting it back in for where x is, so it becomes x squared squared. So he's right. Which, by the way, is equal to x4. Is everybody clear on that answer? Does that make sense to everybody? All right, if you're not sure, then you let me know. All right. Now, domain and range, I'm just going to quickly go over that. The domain of this function would remind you what a quartic function looks like. A quartic function like this looks like a parabola, but it's a little flatter at the bottom than a regular parabola, right? So it looks a lot like a regular parabola, but it's just flatter at the bottom, which means the domain is all real numbers. Could you control up a minute to see the question again? You sure can. So the question was the f of x. That's what we're doing right now. Right? So we're taking the f function, putting it back into the x function. Oh, sorry, into the f function. Yes, Lynette, please go ahead. Mm-hmm. Yeah, no, you're right. And so you're talking about the d, right? The one we're about to do, right? Oh, b. Oh, the b function. Sorry. So we're taking the f function, putting it inside of the g function. The f function is x squared. So go over to the g function, or wherever you see an x, replace it with the x squared. That's all. Okay, good. Thanks for the question, by the way. And of course, the domain we said is XER. The range, just to sort of speed things up a bit, is it's YER, but Y must be greater than or equal to 0. Okay? Hope everybody's okay with that. All right, let's get to Y now. Sorry, D now. So the D function says, put the G function into the G function, right? So whatever the G function is, take that and replace that as the X back into the G function. So look at what Chrysania just did, and Alexander and Donna are agreeing with Chrysania. So it's the x plus 3 function plus 3. That's what it's equal to. All right, let me go back up and show you again. The g function is x plus 3, so take that x plus 3 and put it in for the x. So it's x plus 3 plus 3. Or just simply x plus 6. And of course, that's just a straight line. So domain and range, come on, folks, we don't have to spend a lot of time on this. The domain of this straight line is XCR. The range of this function is YER. All right, I'm not going to spend any time on that. And I'm not going to draw a straight line either. We know how to draw a straight line. Okay, last one is this. And there's a special reason why we're doing this. And we'll talk some more about it in a minute. G to the minus 1 of the G function. But what exactly is the G to the minus 1 again? What does that mean? Does anybody remember what this means? It's the inverse function. Thank you very much, Hussein, Sinduja, Hussein, and Alexa. It's absolute inverse. So I have to get the inverse function. Then we're going to take the inverse function and put it back into the original g function. That's what we're going to do. So we're going to have to find to look at the g function. The g function is the x plus 3. So what we're going to do, we're going to go through the process of, no, Alexander, no. You need to remember how to find that g function. So let's do it this way. I'm going to use y is equal to x plus 3. We did inverses recently, by the way, when we're doing the exponential and the logarithmic functions, because those are inverses of each other. Then we're going to interchange this. So what that means is we're going to make it x is equal to y plus 3. And then we're going to isolate the y. So y is equal to x minus 3. So this represents the g to the minus 1 of x. That's what this is. In fact, let me do that differently. Let's just point to it. All right? This thing here is my g to the minus 1 of x minus 3. So we're going to take the, let's do this right. Let's take the g function right? The inside function is a g function. Put that into the g to the minus 1 function, right? So the inverse function. So I'm going to put it, so let me just remind you now, the g of x, I'm going to write them both down side by side. The g of x function is equal to x plus 3. The g to the minus 1 of x function is equal to x minus 3. Are we good with that so far? So I'm going to put, the order matters. We just learned that a while ago. The order does matter. I'm going to put this g of x function, I'm going to put this function here into the second function. So I'm going to say that the g to the minus 1 of the g of x is equal to, remember, I'm putting the g of x into it, it's going to be x plus 3 minus 3. And the answer, of course, is x when we do that. Now, is that a coincidence that we just got back x? Actually, it's not. FYI. Doesn't matter what the equation is. You might want to take a note of this. It does not matter what the equation is. If you find the g to the minus 1 of the g of x for any function, you always get back x. Because what this is doing is it's taking a function to the result and then taking the result and putting it back in to the function that usually reverses the effect of the function. So it should take you right back to the original x. So that's not a coincidence. And to prove it, we're going to take an arbitrary function. This one takes a little bit more time. And we're going to show that the f to the minus 1 of x is equal to the f to the minus 1 for x for all values of x, meaning that we're going to end up with it being equal to x, hopefully if we do this right. All right? Okay, so this is going to involve a bit of math, so strap yourselves in, folks. All right, we're going to take on a bit of a wild ride here, but you're all grade 12 advanced function students, so don't panic. We should be able to do this. Here we go. So let's first of all find the inverse function for this f of x function. That's our first goal. So y is equal to x over x plus 2 is my original function. And I'm going to first of all flip my x's and my y's, right? Stop me if I'm going too fast. So I'm going to say that x is equal to y over y plus 2. Okay, so far so good. All I've done is I've traded my x's and my y's. What was the next step again when we were trying to get that inverse function? Does anybody remember what the next step was to get the inverse function? Right? What do I need to do next to get my inverse function? Come on, folks. Work with me here. I haven't pulled out the wheel yet. Isolate the y. Thank you, Davina. So let's do that. So Roma says, okay, so we're going to do that right now. So I'm going to cross multiply. So I'm going to get x multiplied by y plus 2 is equal to y. Well, that certainly doesn't do what I wanted to do yet. It doesn't, because I still have isolated my y. I still have y's on the two sides. So what do I do now? Can somebody suggest something else that I can do? Right? I have x times y plus 2 is equal to y. So what do I do now? I want all my y's together, remember? All my y's need to be together on one side. So can you give me some suggestions here, folks? Divide by x on the two sides, Hussein says. Not really. No, I have another idea. Divide by x, so all that would do is it give me y over x is equal to y plus 2. So I have another idea. Can anybody suggest what that other idea might be? How about if we expanded this? So we have xy plus 2x equals y. Right? We'll see why that is useful in a minute. Right? So if I did that, what would you recommend next? Right? Remember I said I want all my y's together. I want all my y's together. What do you think, folks? If I want all my y's together. Okay, so 2x is equal to y minus xy. Okay, so 2x is equal to y minus xy. Okay, what's next? What is next? I factor out the y. Good. So 2x is equal to y into 1 minus x. By the way, can we agree on that? That factoring out the y makes sense. All right, good. And then now we're at the point where we should be able to give us the final value of y, which is, what's y equal to now? What's the numerator? What's the denominator? What's the numerator, first of all? Remember, you're going to divide both sides by 1 minus x, right? Yes? Okay, so let's do that. So 2x divided by 1 minus x. So this, now that you've isolated the y, this is my f to the minus 1 of x. Now, there's one way to prove, there's more than one way, but one of the ways that we can prove that something is an inverse, I'm going to show you that proof right now. The proof, before we use this to find the f to the minus 1 of x, which we will do in a minute, or the f of the f minus 1 of x, what I'm going to do is I'm going to test out this inverse. Let's go back to the original function for a minute here. All right, the original function was f of x equals x over x plus 2. All right, so let me draw a line under this. Here's my original function. F of x is equal to x over x plus 2. Now, I'm going to ask one of you at random to give me any value of x you like. I'm going to throw that to Lance. Lance, any number you want. Try not to get outrageous. Don't give me like 6,200,000. Just give me something fairly. Okay, so Lance says 10. Let's find the f of 10, right? So the f of 10 is equal to 10 over 12, basically. Right? 10 plus 2, which is 12. And of course, that reduces down to 5 over 6. Favorite number, Lance says. Okay, Lance. So all I've done is ask Lance to give me a random number, which he gave me 10. I put the 10 into the function, so it's 10 over 10 plus 2, or 10 over 12, which is 5 over 6. Now, what do you think would happen if I found f to the minus 1 of 5 over 6? What result do you think I would get by doing that? If I put that result, the result is 5 over 6. What do you think I would get if I put that into my inverse function? And you're right. Well, we're going to find that out right now, see if that's right. So that's going to be 2. Okay, let's put that down here. 2 times 5 over 6 divided by 1 minus 5 over 6. That's what we're saying we're supposed to. Well, if we got the right inverse function, this should work. Remember, we just chose a random number here. All right? Okay, so this is going to give me, what is that? 10 over 6 divided by, 1 minus 5 over 6. Can we agree that that's going to give me 1 over 6? Can we agree on that? Right? The denominator, 1 minus 5, 6 is 1, 6. Can we agree on that? Okay, we do. Okay. So how do we divide a fraction by a fraction again? Does anybody remember how that works again? So 10 over 6 divided by 1 over 6. Well, you multiply by the reciprocal. So that's 10 over 6. Let me come out down here with that. That's 10 over 6 multiplied by 6 over 1. Well, surprise, surprise. It's 10. So you could try this with any number, by the way. This is not just because Lance got lucky and picked the number that would work. An inverse function is supposed to reverse whatever a function does. That's what an inverse function is. That's the essence of an inverse function. It takes a result and takes it back to your starting point. That's the whole point of an inverse function. So we're about to come up here and find, it says, show that these two things are equal for all values of x. So here's what we're going to do. We're just going to sort of shorten this a little bit. We're just going to find the f of minus 1 of x. And remember the result I got the previous page? when I found the g to the minus 1 of g of x, I got x is the final result I got. Let's see if we get the same thing here. So I'm going to, now remember what they're asking. I'm going to use this. I'm going to do this one. I'm going to put the inverse function into the original function. So remember how that works, right? I'm going to take my inverse function. I'm going to remind what my inverse function is. My inverse function is this guy right here. That's my inverse function. That is going to go inside of the original function. The original function is this one right here, right? So I'm putting this function as my x into that function. I know it's a little complicated, but you know what? You are strong students, so just work with me here. This is the one I'm going to be putting in, the 2x over 1 minus x, anywhere I see x in the original function. So the original function, remember, is the x over x plus 2. So I'm going to replace all the x's with 2x over 1 minus x. So here we go. Here we go. All right. So let me write that down as f to the minus, I don't know why I'm using yellow, but it doesn't matter. F to the minus 1 of f of x. I'll switch the colors in a minute. So what is that equal to? So remember, is this what we're doing? F to the minus 1 of, what are we doing again? Oh, no, that's wrong. That's the wrong way around. Sorry, that's the wrong way around. Put the f to the minus 1 inside. You know what? Doesn't matter. We'll put the f to the minus 1 inside. That's what we said we're going to do. All right, so make sure I got it right this time. I'm putting the inverse function inside of the original function. That's what we're doing. So the inverse function, I'm reminding you, is the 2x over 1 minus x. So anywhere I see x, I'm going to put that. So 2x over 1 minus x. Get back to black here. Oh, sorry. Yes, there's a question. Yes, Quinn, please go ahead. It's hard to see. Yes, I see that right. Yes, I'm going to switch to black now. Is it the same thing, Quinn? Oh, okay. Yes. Yellow is hard to see. I'm sorry about that. So remember what my function is. In fact, let's put the two of them side by. You know what? Let's put them both side by side. The f of x function, actually, f of x function is right here, so it's not too far away. And the one that I'm going to put into it is this one right here, which is 2x over 1 minus x. So I'm going to go let me not use red, I'm going to use black. So 2x, that's not black. Okay, try that again. So 2x over 1 minus x, right? That's my x on top, over the x plus 2. So it's 2x over 1 minus x, right? And remember now, this is plus 2. So this is kind of good practice for us to see. All pass, please. Yes, Joshua. Right? I'm taking anywhere I saw x before, I'm putting in the inverse function. So the x becomes 2x over 1 minus x, and this other x becomes 2x over 1 minus x again, plus 2. All right. Folks, hang in there. Hang in there. We can do this. Next step, right? Treat this as if this was any other rational function. What's my next step, folks? What do I do next? All right, so it's 2x over 1 minus x over 2x over 1 minus x plus 2. Come on. I want to get this done before the end of the class here. What's my next step? At the bottom equation, find a common denominator. So let's take that 2x on top over 1 minus x over the common denominator, which is 1 minus x. And on top of that, we're going to have 2x, hopefully you're going to agree with me on this, plus 2 into 1 minus x. I'm going to hope that everybody is okay with what I just wrote down. All right. If you're not, let me know. So Donna, does that, not just Donna, I should be picking on Donna. Does that line make sense, what I just wrote down, with the common denominator of 1 minus x? Okay. How about everybody else? Does that make sense? Okay, good. So let's keep going here. So on top, we still have the 2x over 1 minus x over, on the bottom of this, we're going to have 2x plus 2 minus 2x over 1 minus x. Let me bring this over to the other side now. So on top, I have 2x over 1 minus x over what looks like it's just going to be 2 over 1 minus x. So it looks like to me, right? Because those 2x is going to cancel out. I'm just going to have to do 2 over 1 minus x. We're going to do the same thing we did before. We're going to multiply by the reciprocal. So I'm going to have 2x over 1 minus x multiplied by 1 minus x over 2. Okay? The 1 minus x's will clearly cancel each other out. I left with 2x over 2, which is x. Okay? So that's really what this is all about. That is simply showing you that regardless, and I'm not going to do it the other way around, but it will work out to be the same thing. This is the one time that if I were to take the other way, which is to find the f minus 1 of f of x, I'd still get x. Any function that you compose with its inverse, okay, Natasha, always just gives you back your x. That's always the case. Now, I didn't get to the wheel today because I really want to get to this question. This is kind of where it kind of gives you an idea of where you could actually apply. How do we get the second? No wheel. Oh, yeah, listen, I got that wheel ready for you tomorrow. You don't worry about that, right? Let me go back to what you just said now, over 1 minus x. Okay, just go back here. So what happened to the 1 minus x's will cancel each other out is what we're saying. Okay? 1 minus x, 1 minus x, they're both common factors. Okay? How you got, sorry? Oh, I just took the denominator here and flipped it over and multiplied it by the top. Oh, over here? Oh, okay. So this up here, I'm talking about up here, where I'm pointing to now. Okay. So this is the composition part of it. So my inverse function is where's my inverse function? My inverse function is 2x over 1 minus x. That's my inverse function in this black circle right here. Anywhere I see x in the red box, I'm going to replace it with 2x over 1 minus x. That's what we're saying. So the x on top becomes 2x over 1 minus x, which is what this is, 2x over 1 minus x. The x at the bottom is going to become 2x over 1 minus x, and then plus 2. So I'm just replacing each of those x's with the 2x over 1 minus x, is what we're saying. Hopefully that helps at least a little bit. Okay, let's see if we can get this question done. All right, and then we can wrap up. So the formula for the circumference and area of a circle is something you're familiar with. The circumference is, of course, 2 pi r. The area is pi r squared. All right, that's just formulas that you knew. You're welcome, yeah. That's just formulas that you would have known from back in elementary school, actually. Develop a composite function. So here's where we're going to put the composite function principle to the test. Develop a composite function in its simplest reduced form that could be used to determine the area of a circle based on its circumference. So here's what we're saying. Yeah, I know we can find the circumference if you give me the radius. I know you can find the area if you give me the radius as well. But can I take the area function and using the circumference, if you just give me the circumference, can I find the area right away? Do I have to go through the two functions or can I just put those two functions together? That's what we're about to find out, right? Can I plug the C function into the A function? So at the end of the day, I have a function that gives me area based on circumference. It actually is possible. So here's how we're going to do it. Hopefully everybody understands exactly what the principle is. Take this C function and somehow stuff it into this function for A. What's the common link between those two functions? What's the linking variable between those two functions? What do you think, folks? What links those two functions together? The pi and the r, true. Well, let's just focus on the r for now. Let's focus on the r for now. I'm going to take that C function. I'm going to isolate the r, right? So here's what the function says. C equals 2 pi r. So I'm going to say that r is equal to C over 2 pi. All right, that's just rearranging the formula. So Alexander and Roma, you're both right. So can I now take this information and plug that into the second function so that all I have is an A function that references C rather than R? Yes, I can do that. So my A is therefore equal to pi, not by R again, but by C over 2 pi squared. So at the end of the day, I should have a function. Can you have also isolate the pi and sub that in for pi? I never thought of that actually, Hussein. That's actually something I should look into. Let's just say that for now. All right, but let's just keep going for now. That's something that I really should look into. All right. At any rate, this now, well, actually, you know why I don't think that might work though, because if you isolate the pi and the r, you would have kind of a little problem because this pi times r squared. So I'm not sure how you would put that in. All right, so let's keep going here. So let's just see if we can simplify this sum. So this would be pi times c squared over 4 pi squared. Hopefully that makes sense. I'm squaring the 2 and I'm squaring the pi. I'm squaring the c on top. The pi on the outside here doesn't get squared because it wasn't squared in the first place. So let's see if we can reduce this down some. So that should be equal to, that's my A. That's A now based on C. It's not based on R anymore, it's based on C. One of these pi's are going to cancel out with one of these pi's here. So I'm going to be left with 1. So I should end up with this. C squared over 4 pi. C squared over 4 pi. Another way that we could write this, just for the record, is C over 2 squared times pi. All right, that's one way we could write it as well. So how is this useful? Let's look at the question down here and then we can wrap this up. And then we'll probably have to go over this somewhere tomorrow. As I said, there's no homework tonight, but you do have to submit that homework that we talked about earlier on. Using the composite function obtained in part A, so this is the composite function we got in part A right here, C over 2 squared times pi, right? And that's a function that links circumference directly to area, right? Give me the circumference now. I can tell you what the area is based on the circumference. So watch what this says. Use a composite function obtained in part A to determine the exact value for the area of a circle, given that the circumference is 8 pi centimeters. Remember that units, remember the units in your answer. Okay, so this thing says that, now one way to do this, is to figure out what the R is, then use that R to put it in the second equation, or just use the composite function. The composite function brings those two things together and says, take the C, divide it by 2, square it, and multiply it by pi. So it says. So we're going to do that right now. Here's my C, which is 8 pi. I'm going to say 8 pi over 2 squared multiplied by pi. That should give me what my answer. Did I do that right? Hold on. C squared over 4 pi. That's wrong. That's wrong. Oh, no, it's not wrong. C squared over 4 pi. Say that is wrong. So it's over 5. Hold on. C over 2. Oh, 8. Hold on. 8 pi over 2 squared. Yeah, okay, so we're good. We're good. Am I missing a pi somewhere? You know what? I think I did. That pi should be at the bottom. Sorry, this is over pi. I'm sorry. C squared over 4 pi. This is not quite right. Let me fix this. I know something was wrong. So it's C over 2. I know I'm rushing. It always happens when I'm rushing. Times 1 over pi. All right. It is 1 over pi. Yeah, you're right. You're right, Roma. You're right. It is 1 over pi. All right. You know what, folks? It's 140 or 240. I need to finish this up tomorrow because we have to finish this up and then we're going to do some examples. So sorry about that. I rushed. I didn't really pay as much attention as I should have and then messed up. So we'll start this all over tomorrow again and we'll finish this up. All right. We'll not start from the beginning, but start from where we left off at this point. All right. Meet me in block 4, please. I'll see you over there.